introduce hyperbolic second function. So the original hyperbolic second function should be like this, that the original figure is just like this. So this is the original hyperbolic second function. But as you may see that actually, if we focus on its original domain, we will not have a one-to-one property. So that we need to retrieve its domain and just focus on this part. So for this, if the original domain, we will retrieve it to 0 to positive infinity, then its range will be 0 to positive 1 included, right? From zero included, right? Then ended at positive infinity, but its range will be 0 not included to 1 included, right? So if we have this, then we can have hyperbolic, the inverse of a hyperbolic function, or arc hyperbolic. Sorry. Going back. Hyperbolic second. Arc hyperbolic second will be like this. So its range, its domain will be 0 not included to 1, not included to 1. Then will be mapped to 0 included to positive infinity. So this part is hyperbolic second function, arc hyperbolic function. So only these two functions, we need to have retrieve its domain. Then actually, I will not illustrate all of the 6 hyperbolic functions, but you can understand the concept by reusing the idea you just learned from trigonometric function. Then I will show you some special property that this is very interesting, that arc hyperbolic second function x is equal to arc hyperbolic cosine function of 1 over x. It's very interesting. This result is very interesting. Why I say it's interesting? Because you can see second hyperbolic second function is the protocol of hyperbolic cosine function, right? We already know this, right? And you can find the position here. This is x. This is 1 over x. And it's also its inverse. Then you can see the corresponding relationship is here, and the corresponding relationship is here. So we just has the exact relationship between these two inverse functions, but with different input. This is x, this is 1 over x. So I will show you why we can have this. Because when we want to find, you can just see that here we are trying to find the inverse of hyperbolic second function, right? If I write this notation, actually I'm trying to find the inverse of hyperbolic second function. So when we just try to find an inverse function, did you remember we also talked about that? If you have an inverse function, you will just have unique. You will not have 2 or 3 or more inverse function. You just have one, right? Only one inverse function. So once I find some function composed or be composed with the original function, and then I can get identical function, and then it's lucky for me to find the inverse function. So you can see right now I am trying to find hyperbolic second function's inverse function. So if I can find some function composed with its original function, then if the answer can be x, did you remember I just know it down here? F composed F inverse will be x, right? F inverse composed F be x. And the inverse will be the unique one. You cannot find more than one inverse function. So if I try to compose some function, and then finally we can get it is x or the so-called identical function, then this part will be its inverse function. Can you understand that? Let me just repeat it again. If I try to find, I already know it's a one-to-one function, so we can have inverse function for hyperbolic second, right? Right now I'm trying to find its inverse function. My way to find the inverse function is I trying to let the original function to compose some function, then it will become identical function. Then I will say the final one will be the inverse function of hyperbolic second function. So that I try to compose hyperbolic arc hyperbolic cosine function here. Then you can see I will check if it will really be identical function. So after I compose them together, and you can see this is hyperbolic okay, so you will see it will be 1 over hyperbolic cosine function, then of hyperbolic arc hyperbolic cosine function of 1 over x, right? From here to here, no problem, right? Because hyperbolic second function is the protocol of hyperbolic cosine function. So I convert it from here to here, right? 1 over blah, 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 right? Then you can continue to find that will become 1. You can see this is a hyperbolic cosine function. This is the arc hyperbolic cosine function. When I compose them together, will become 1 of x, right? This part will just, because they're identical, right? Then the result will 1 over x, the result will x. So luckily we find when we just compose them together, we can have an identical function. That's it. That's it here, right? So we can say, so that we, therefore we will say arc hyperbolic cosine function of 1 over x is hyperbolic second function's inverse. Right? So it's a tip. It's a tip because we can have the uniqueness property for the inverse function. So once we can find some function composed with that together, and then we get identical function, then we will say it is the original function's inverse function。我很快讲一下，就是说这个特质很特殊啦。我跟大家讲，这里考试也未必会考，但是我觉得这个特殊性让大家稍微回想一下，正反函数的时候我们怎么说的？我们说，如果它有1对1，我就可以保证它有反函数。它有反函数呢，它的合成函数合成之后一定会变成 identical function。所以就从这个，而且合成函数反函数呢只会有1个，不会再有第2个了。所以我们就用这样的理由呢，当我要去找出它的反函数的时候，怎么做呢？如果我让它可以合成之后变成 x 的话，就很幸运，我们就说这个它是它的反函数。所以刚好我们把它凑巧的把它合成出来之后，它刚好是 identical， 所以这个它就是它的反函数。好，这道理让大家知道。所以同样的事情会发生在哪里 ？Hyperbolic cosecant, hyperbolic cotangent. You can just find a similar result. Then I can also show you, and just here that you can follow the same property. Then you can get this one. Then you also have this one. Also follow the same idea. You can just refer to here, then you can find these 2 results. Okay. Then we will go into the derivative and the integral. I will show you the first one. The first one is this one. So, did you remember this one? Did you remember this one? What is the result? Or maybe I can. This is 1 over square root 1 minus s squared. No, this is inverse, right? Did you remember this? Which I learned for its inverse function for the arcsine function, right? But you can just notice that there is a very small difference here and here. So next time I also ask you to remember that if I just want to integrate this part, then we can get this part, right? You want to integrate this part, and then we can go back to get this one. So similarly, if you just face the problem to integrate this, then you can get arc hyperbolic sine function. So that's why I just say that there are some formulas with tiny differences. Then sometimes it's also hard for you to memorize them at the same time at once. But please just write down them again and again, and finally you will find the small differences among these formulas. Okay, and then the second one, I will show you the second one. The second one is this one. I try to differentiate hyperbolic cosine function. Then the result is 1 over square root of u squared minus 1 du dx. So please also notice that actually this one is also different from this one. See, this one is 1 minus s squared or 1 minus u squared. But here is u squared minus 1. So different. Very small differences. Then u must be larger than 1. Then if you want to prove this, how to prove it? Again, we will let the original function will be hyperbolic cosine function. Based on this, we can have f prime x is equal to hyperbolic sine function, right? I proved this for you earlier last week, right? Then we also have f inverse of x is hyperbolic cosine function's inverse. So we have this. Then by theorem 7-1, we can have, when you want to get the f inverse prime of x, you should do f prime blah blah blah, but use f inverse of x as the input. Did you remember it? We already used this property several times, right? If you want to get the inverse of f of x derivative, then you should try to find its original function's derivative. Then use the inverse function as the input for this part, then take its practical value, right? So you can see by following this, f prime x will be hyperbolic sine of, then use hyperbolic cosine inverse as the input, right? You can see here, exactly here, so it would be hyperbolic sine, and I use this as the input. I use hyperbolic cosine function as the input here. Then try to convert it. We can try to convert it by, since hyperbolic cosine square x minus hyperbolic sine square x is equal to 1. So we can convert it into square roots of hyperbolic cosine square minus 1, right? But use hyperbolic cosine as inverse as the input, right? By using this formula, you can just convert it from here to here, but still use hyperbolic cosine inverse as the input for this part. Then again, you can see there are two x just happen here. So finally, we can get the result is 1 over square root of square roots minus 1. Right, so actually these tips for getting the derivative of its inverse function are very similar. Also, all of them just follow the theorem 7-1. Okay? So this is the second part. And the third part is for the rest parts, I will not prove everyone. I just show you the result here. Hyperbolic it will be 1 over u squared du dx. Then if you focus on this one, hyperbolic cotangent inverse function, then you can get this. You will notice that actually these two ones are exactly the same, right? But how to differentiate, how to just separate these two parts. One is its domain is this one, and the domain is this one. Absolute value based on its absolute value. So this part will be determined by its absolute value. 所以你看这两个啊，这两个微分下来是长得，你如果不去看这里的啊，你会发现它长得一模一样。怎么区隔呢？就看你的 U 的范围。如果你的 U 的范围是属于你反过来，如果 U 的范围是这个范围的话，当你积分这个东西的时候，会回到 hyperbolic tangent 的 inverse。如果你的 U 的范围是这个的时候，你的积分这个式子的时候，你回到的结果是 hyperbolic cosine inverse function。So depends on your x value of U. Then we still have the rest two ones that minus U times then the last one. So actually no worries. For the rest four ones are a little bit complicated, but maybe when we just have our intern exam or our quiz, we will not include these four ones. But please, at least you need to remember this. You need to remember this, okay? But for the rest four ones, I think for you it's a little bit complicated. But of course, after we have these properties, did you still remember that I asked you that when you just see the formula for differentiation, please just think the opposite way. You can just get its integral formula. If differentiation is this way, then integral will be followed this way, right? Opposite. So for its integral, we will also have several formula. The first one is this one. It will be hyperbolic sine function of U over A plus C. A must be positive. The second one is square root of, when we just integral the square root of U squared minus A squared, and we just try to integrate its particle, then we can get its arc hyperbolic cosine function of U over A plus C. Then U must be larger than A, larger than 0. Then the third one is du over A squared minus U squared. Then we will have two results. One is this one. So as I told you, actually the result will depends on your domain. So if your U squared is less than A squared, then you will get this result. If your U squared is larger than A squared, you will get this result. So as I told you, the range of U will determine the final result. And last time I also told you that actually this formula come from this one, right? So they are look alike, right? You can see here, this is square root 1 over square root of 1 plus u squared. But here, we are trying to get the integral of 1 over square root of u squared plus a squared. So you can see they look quite similar. So that's why I also told you that here we just let u become v over a, right? With this, then we can get this. Just what I show you for the integral in the inverse of the inverse of the trigonometric functions. 我们在反三角函数的时候，你记不记得我也类似做过这样的事情？这边讲的是比较快，不过你会回想我上次在跟你讲这里的时候，有没有？我也是先证了什么反三角函数，就是sin的反三角函数的微分，我们得到1等于1除以根号1减掉 u 平方 du ds。我们先有这个结果，然后呢，我们顺着把这个 u 呢取代成什么 v 除以 a。所以有这个公式把 v 除以 a 代掉这个 u 的话呢，你就会得到相对的这个结果了，很像的结果，所以在这里也是同样的方法去处理的，你就可以得到这个公式，所以会让你觉得，看起来很像，事实上它们是同一个，只差别是它一个比例的关系而已。Okay, so I will give you an example that in case you just face the problem of the question of trying to integrate 2 over square root of 3 plus s squared ds. So try to find these 3 patterns to map your problem. That you can see here, it is close to this pattern, right? You can see this is close to this pattern. When I just let a is equal to square root of 3, then u is x, right? Then we can have this part is a squared, this part is u squared. So once we assign u to be x, then we can immediately get this one. Then du will become dx. So based on this, you can get the result will be based on this. Let me just make it smaller. So based on this, you can follow the result with 2 because it's a constant, right? Here is a constant. We can move it out of the integral. Then the rest part is 1 over square root of a squared plus u squared. So it will match this formula. So the result will be hyperbolic, the arc hyperbolic sine function of u. U here will be x, right? Here's u, so we should have x because u is equal to x. Then over a here is square root of 3 plus c. That's the final result, right? So you just simply use the formula. You can get this one. Okay. So this part is for session 7. Okay, so we almost finished the whole chapter 7. So I plan to hold a first quiz. For this semester, I plan to hold a first quiz on next Thursday. So next Thursday will be around March 20. Let me check. March 28th. Is that okay? Or how about this week? Is that possible? No. Okay. So I think I give you more than 1 week to prepare, but we will not include sections 4 as a remember. Section 4 we will not include. We will not include it, but for the whole section 7, as chapter 7, we will include it, but not 7-4. We will not include it. Okay. Okay, if no problem, we need to faster. We need to go faster. So is any problem here? If no, we will start section chapter 8. Chapter 8, we will talk about some techniques for integration. Okay, and we just section 1 we already learned it, because section 1 is talking about the substitution. Next semester we just learn how to integrate some function by using the substitution technique, right? So this semester in chapter 8, we will skip that part. But we skip that part. That doesn't mean it is not important, because you already learned it. So in the future, after you just finish the study for chapter 8, you need to put all techniques in your brain. So if you face different problem, different question, different problem, you need to use different techniques to deal with. Okay, so later I will show you for which case you need to use these techniques, for which case you need to use these techniques. So this is what we learn in chapter 8. So the first important part is the integration by parts. This is also very, very important in calculus, integration by parts. So in the past, if you encounter such kind of integration, this is multiplication. So is that just like this one? No, it's not. For addition, it's fine. For multiplication, it's not. Right? If this is addition, this operator is addition, it's fine. Right? But if it's not addition, it's not addition, it's not subtraction, you cannot just cover it just as the right hand side. So if you just face this problem, then if f of s can be differentiated repeatedly, and g of s can be integrated without difficulty, then you should try to think about integration by parts. But integration by parts does not always work. Sometimes it also have some problem. So later I will show you also. But integration by part indeed is a very important technique for integration. So you need to pay much attention to this part. So how can we have this? If you still remember that if we try to differentiate this one, right? We know it will be f prime x times gx plus f of x times g prime of x, right? Last semester we learned this, right? When these two terms comes together, we try to differentiate it, then the result will f prime x times g of x plus f of x times g prime x, right? Then we just integrate at both sides, right? Because this is addition. This is addition here, right? This is addition here. So we can just separate it like this, right? Because there is addition. So we can keep this equation whole, right? Then, okay, for this part, you can see this part is differentiated first, then integrated later. So based on the fundamental theory, we can get f of x times g of x back, right? We differentiate this term first, then try to get its integral back. Then we will let it come back to the original form, right? For the right-hand side, we can get it will become this one, right? So that we can just move this term to the right-hand side, so that we can get integral of f of x times g prime of x dx is equal to f of x times g of x minus f prime x g prime of x g of x dx. Right? So you can see this is the final result we want to have. So that means original you just face an integral for f of x times g prime x. Then it can be converted as f of x times g of x minus integral of f prime x times g of x. Right? So you can see from the viewpoint of f of x, you can see f of x will become f prime x. From f of x to f prime x, that means differentiated, right? Differentiated. But g prime x, from g prime x viewpoint, we face another new integral form about gx. G prime x to g of x. Here, you can see from here to here, we are talking about differentiation, right? From g prime x to g of x, we are talking about integration. So that's why we will say, if you encounter two terms times together, you want to calculate its integral, f of x should be differentiated repeatedly. Then g of x also need to be integrated repeatedly without difficulty. Because as you know, that sometimes it's not that easy to get the integral form. So we need to make sure when these two terms comes together, when these two terms comes together, you need to make sure f of x should be differentiated repeatedly without difficulty. For g of x, you also need to have no problem in integrating g of x, no problem, because you just change the integral form from this to this one. So if we just let u become f of x, then you can get du over dx is f prime x. So you can have du is equal to f prime s dx, right? So similarly, if v is equal to g of x, you also can get dv is equal to g prime x times dx. So through this, you can just also change the notation, become integral. Okay, f of x here, you can see f of x here, right? F of x, I will use u, right? Just go with me one by one. F of x here, f of x here, it will be u. Okay? Then you can see g prime s dx. Where is g prime s dx? Here. G prime s dx here times dv, right, is equal to f of x times g of x. F of x is u, g of x is v. So we will have u times v, right? Then minus integral f prime x. F prime x is f prime x is here. F prime x times d of x is here, so it will be du. And g of x here will be v. So finally, please just keep this in your mind, that integral, so in summary, integral u dv should be u times v minus integral v du. This is a very important result. So we just take 10 minutes break and then come back to the classroom. I give you the first example. For example, if you want to integrate x cosine x dx, right? It's a typical f of x times g of x, right? So that I will show you the positive procedure, a correct procedure. Then later I will also show you some wrong procedure. Then I hope you can just identify which one is you should follow. Okay, so the correct one is this one. Then, okay, in the beginning we need to find which one is u, which one is dv. You should assign that. So for example, if I assign u as x, then for the rest part as du, dv, right? Because this part is dv, right? So we just have a mapping that this is u, the rest part is dv. Then we try to find what is u, what is v, right? So If so, if follow this, I just let u is equal to x, then dv is equal to cosine x dx, right? But here we need 4 elements. Based on this, we need 4 elements, including u, v, du, and dv. So just remember that if you want to apply integration by part as your the technique of integration, you need to clarify, you need to identify these 4 elements. So right now, if I assign u is equal to x, dv is equal to cosine x dx, you need to try to find, for u part, you need to find du. For v part, you already have dv, so you need to try to find v. Okay, so based on this, so we already have u is equal to x, right? So that du over dx is equal to 1, then we can have du is equal to dx, right? So far we already have u, v, and dv, right? But for the v part, since we already have dv is equal to cosine x dx, so we try to convert it into dv over dx is equal to cosine x. So v will be what? Sine x, right? The simplest one should be sine x. Of course, you can say sine x plus 1, sine x minus 100. We just find the typical one, sine x. Because if dv over dx is cosine x, v the one possibility is for v is sine x, right? So right now you can see we already have 4 elements. Here is for du, here is for v, right? So right now 4 elements are already there. Then we try to fit it into this one, so that it will be u times v. U is x times v is sine x, right? Then minus integral, then v sine x times du is dx, right? So from this one, from this integral form, from this integration form, we convert it into the right hand side as this form. So you can see x times sine x computable minus integral sine x dx. So right now this form is also computable, also integratable, right? So what's the result? This one will be what? This part? Cosine. Minus cosine. Minus. So it will be, it is positive, negative, positive, right? Is will be plus, right? So that we can get the result will be s sine x plus cosine x plus c. Right? Let me just remind you again. Here, if I assign it's u, it is u. U is equal to x. Then For the rest part, I assign it du dv. Then if you already have v, you already have u, you already have dv, you need to find some way to get its du for u part. You need to find somewhere to get its v part. So you can have these four elements. But through this, then you can find the original integration form is this one. Then you convert it as this one. So original one is not integratable. It's not computable. But for this one, it's computable because it's just simply integrate sine x in terms of x, right? So it's integrable so that you can get the final result just like this, right? But you may think, how about some other choices? Some other possible choices, like what? So again, I just repeat the problem, repeat the question here again, right? You may say, okay, can I just assign this part as u? Then I assign here is dv. Can I try to do that? Yes, we can try to do that, right? So if so, just follow the similar rule. Then maybe I can make small. I also do it like this. By following this, I have u is equal to s cosine x. Then dv is assigned to dx, right? So again, 4 elements. Right now I have 2 elements, but I need to use these 2 ones as the clue. Then we can get the du for this, and we need to get v for v part. So for this part, it's quite happy, right? For this part, because dv over ds is 1, so that v is equal to x. This is a happy ending for v part, right? It's a happy ending for v part. But this part will cause some big problem, because right now you need to get du, right? So the only way for you is just differentiate it in terms of x, right? So the result will be cosine x minus x sine x, right? Then du will become cosine x minus x sine x, then dx. So again, you also have 4 elements. Element 1, element 2, element 3, then element 4. Of course, you can have 4 elements, right? Then you can try to follow the integration by parts. Then it will become very complex. For example, okay, I can try to do it for u. So the result will be u times v. U is s cosine x times u times v. U here, v here, right? Integral v, right? V and du. V, then du is cosine x minus x sine x, then dx. So after you convert the integration form from the left hand side to the right hand side, you will see this form becomes much complicated. 经过这样转换，你发现这个积分是变得更复杂。So it's not a suitable conversion. See, you need to face such a complicated form and to integrate. So it is not a good one. It is not a good one. So it's not suitable. So I want to show you is, of course, you have many choices. You have many choices for the assignment, right? Like here, I simply assign u as x and dv as cosine x dx. You also can possibly assign u as x times cosine x and the dv as dx. But different choices will cause different converted form. So if you follow this way, I'm afraid you cannot make it. But if you follow this way, you can get the final result just like this one. So that's why I say, actually, sometimes if you choose integration by parts, normally, if you are lucky enough, you can get a simpler integration form. However, if you choose a wrong way, maybe you will make the calculation become much complicated. Okay, I will show you some other examples. That, for example, in the past, we didn't face this problem. Did you remember? Maybe I can give you a verses that integrate exponential function. What is the result? Also exponential function, right? We learned this before, but we try to integrate exponential function, and the result will be still exponential function, right? But we didn't try to integrate logarithm function. Right now, through the help from the integration by parts, we can deal with this problem. Okay, so again, then we can try to let u is equal to nx, then dv is equal to dx. So if u is equal to nx, then dv is equal to dx. So through this, we can immediately get du over dx is equal to 1 over x, so that we can get du is equal 1 over x dx. Okay? Then four elements principle, you must find u, v, du, and dv. So through this, since dv over dx is equal to 1, so that we can get v is x. Right? So let me just write down the formula for you. Integrate u dv is equal to u times v minus v times du. Integral v du. Right? So right now we have four elements. Four elements here: u, dv, du, and v. So that also follow the formula, we can get ln x is u times v x minus integral v times 1 over x dx. Right? Through this. So we convert it into this one. So you can see right now it becomes simpler. This part cancel. Then finally we will get ln x as times lnx minus x, because here we can cancel it, then plus c. This is your final result. So finally, you can also memorize it that this integration will be this one. Okay, so you can see through this one, you can get the integration results for lnx. But if you do not apply the integration by part techniques to this problem, actually you cannot get the result. Right? Okay, this is second one. So the third one is this one. This is also a very important one. So that I need to show you that you will face this problem. So please remember the statement for the problem will not always use u and then dv. Sometimes you need to change it, the order by yourself. You need to try. It is not necessary that when the problem just come out with the sequence of the assignment. For example, this one, okay, maybe intuitively I will show this is u, this is dv. So you can find one fact that, did you remember when two terms comes together, one term must be differentiated repeatedly, without any difficulty, right? But the other term is much important than FIS, because the second term should be integrated without difficulty. Because sometimes when we deal with the integration, that is much harder. Than we deal with differentiation. So when you just assign it, you need to notice that when you assign some form for u, you should differentiate it without any difficulty. It's much easier. But if we want to integrate it without difficulty, normally we will choose like e exponential, because when we integrate its exponential, we always can get exponential function, right? But if it's too difficult to get the integration, you need to think about changing the order. For example, move this term to become the first term and the s squared to be the second term. Okay, so sometimes you need to try. It is not necessary that based on this sequence, you always need to assign this is u, this is dv. It's not necessary. OK， 我要讲的是说哈，你不要以为题目写这样，你就一定是这边是 u， 这边是 dv 哦哈。有时候它题目可能故意给你放比较适合放的，摆在这个 u 的v 的部分，把你摆在前面，然后这个像是 s 平方给你摆在后面，你要自己去想办法，因为乘法是可交换的。可交换的时候，你可以自己换那个顺序去尝试哈，你不要认为说他一定很好心的帮你摆好这个顺序哦。但我现在秀的例子都是刚刚好了哦。Okay, so let's just look at this example. Okay, maybe we need to go faster. Then we will say u is equal to s squared. Then also we have dv is equal to exponential function times dx. So based on this, we can quickly to get the result is du dx is 2x. Then we can have du is equal to 2x times dx, right? Then for this part, we have dv over ds is ex. Then v is, so here v should be what? Here, e exponential function, right? So that we have 4 elements. this element, the third element, the fourth element, right? So based on this, we can have SU times V minus integration of V times 2s dx, right? So we will become, the problem will become s squared ex times minus 2 times s exponential function dx. Not yet finished. Not yet finished so far. Right now you can notice here. You can notice here. This form to this form. Did you notice anything? Yes. So far not yet finished. But you just find some fact. Okay. X squared becomes x. So the power from 2 become 1, right? Its formation is still the same, right? So we can just insist the same rule again. Just do it again. Do it again for, you can just try it like here again. Here is V, here is dV. So again, maybe we will think about it, the result will become constant, right? If you just do it again, we will weaken the power from power 1 to 0, right? So eventually this term will be vanished. If this term vanish, then you will see the integration function calculation, and the result is exponential. So I will not do it again for you, but you can just try it by yourself. Then finally, the result will become s squared e to exponential function minus 2x e to the power x. This is the final result. So please just do it again. Here, you need to repeat the process again, just like this, and then you can get the result. So you can simply find, okay, for the first term, we can differentiate without any difficulty, right? S squared. So if, for example, if here is 2, right? Here is 2. You need to repeat the process twice. How about if here is 5? So maybe we can just have a quiz just like this, 100. And then you need to process it 100 times, right? Can you understand me? 这是2次，对不对？2次经过1次，分布积分integration by part， 你会变成1次，再1次它就变常数了，所以常数一万不见了，以后就可以积分，对不对？那如果这题目出成5次，或者出成100次，你就会想象你要做这种动作做100次，或者5次，对，非常这个 power。但是你只要耐心的做下去，它一定会得到结果。你只要观察出它的这个顺序哈。Okay, this is the second example. And then I will give you another example that integrate. So by following the previous rule, we assign this is u, this is dv. So again, we will have u is equal to e to the power x. Then we have dv is equal to cosine x dx, right? So based on this, we will have du is equal to e to the power x times dx. This time I just do it faster. Then with the v part, we will have v is equal to sine x. Okay, so I just speed up. So right now I have these four elements. Then following the formula of the integration by parts, we can have e to the power of x times sine x minus sine x times exponential function times dx. So let's just stop here for a while and just take a look at this result. You can see exponential function times cosine x. Here is sine x exponential function x. So maybe you will doubt if I just assign it again. For example, here is vu, and this part is dv. It will become endless loop, right? Because sine becomes cosine becomes sine, and just like this, I just do it again. Will I just face a repeated problem like from sine and come back to cosine again? Yes, it will. So I will do it again and again. That will become finally, okay, you can just do it again. So you will assign for this part. For this part, you can do it again. Then finally, you can get that. Let me just focus on this part for you. Wait, let me just use the eraser. Okay, so this time I will just only focus on integration. Okay, this time I just focus on this part. This time I focus on sine x e to the power of x dx. So this time I focus on this is u, this is dv. So I just do it again. Then u is equal to e to the power of x. dv is equal to sine x dx, so that I can have du is equal to exponential function times dx. Right? This part no problem. For the v, what is v? V will be minus cosine x, right? You can see if v is equal to cosine minus cosine x, when I differentiate it, I can get sine x back, right? So, and then we can have u times v minus cosine x, right? Minus cosine x times dv. dv is this is u, this is v, then v, then du, right? du will be exponential times dx. So here, minus, then we can have minus exponential x cosine x plus integral cosine x exponential x dx, right? So this part will be replaced by this part. So we can put it together that the original one is this one. It will become exponential x sine x minus, don't forget here is a minus, right? Minus this term. So it will be minus exponential times cosine x plus integral cosine x e to the power x dx, right? So eventually we can get exponential x times sine x plus exponential times cosine x minus integral cosine x exponential x dx. So you may think, wow, we need to replace u and v again. No, right now we just simply put the term to the left hand side. So finally, we just put this term to the left hand side. So totally we have 2 times this term is equal to exponential sine x plus exponential cosine x. So that the Fraser result for this term will be 1/2 times this one. Okay, so this is another tip. You just do it twice, but move the same term to the left hand side, and then simply just move the constant from the left hand side to the right hand side, and then you can get the result. The final result should be this one. Okay, so we still have time. Maybe I can show you that right now we already have this, right? We have this formula. But it seems that it's useful for the indefinite integral, right? Because we don't have the limit for the integral. So it seems that it works for the indefinite integral. However, the same rule also can be applied for the definite integral. So that means if there is a limit here, it also works. It still works. Okay, you can see here, if without the green color, you can see it's just simply for definite integral. But for definite integral, it also works.就是 integration by part。虽然我刚刚看的都是一些什么不定积分，不定积分就是积分出来最后一定是一个式子，你要加一个习题的嘛。但是它一样的也可以用在定积分啊。你记不记得我们当时在讲定积分的时候，有2种做法，一种是你直接如果换的这个，你记得要把这上下的上下阶要换。但是这是不定，这是定积分的时候可以这么做。它还有一种做法是什么？你先不要去看它定积分的范围，你先把它当做定积分来做运算，运算完之后再把 那个上下界也不要上去，这一定也这样可以做Okay, then actually in our textbook there is a term it is just like core tabular integration. So what is tabular? Tabular comes from table, right? You can just make a table, then try to get the integration. Then when we talk about tabular integration, actually it's not a new technique. It's basically it's just based on the integration by parts. So I believe you already find that if I ask you to calculate this one, we will face f times g minus integral f prime times g ds. So did you notice that from f become f prime is about differentiated, right? From g prime to g is about integrated. So there's no wonder we also focus on two functions comes together. One is repeatedly differentiated without difficult. One is integrated repeatedly without difficult. So you can see if we continue to convert it, you can expect f prime will become f double prime. But g will become integrating g. So if we continue to do that, you can see that will be f times g times, we continue to convert it, become f prime g minus integral f double prime g integral rotated. Okay, sorry, this notation is invented by myself. Newton didn't invent this notation. 牛顿没有发明这 S 哈，这是我自创的。你有没有注意到这个？我从这里再转到这里的时候，你就可以期待这个 G 啊会往上再提升一个，然后 F prime 呢会再被微分一次，所以一个是往上，一个是往下 ，F 会一直被微分下去，一直微分到什么时候 ？Constant 变 zero。但是 G 呢，你要注意它的积分要一直能够可以积分，所以这个式子可以一直这样子推演出来。OK， so you can see our f will from f become f prime, from f double prime, then eventually we expect it can become zero, right? Like exponential to the power of 5, x to the power of 5, then you can continue to differentiate it to 0, right? But for g from g prime to become g integrated once, then integrate twice, right? So based on this, you can continue to do that. So when we just make a table, then we just show f of n is the derivative. Then the second part is g of x and its integral. So for example, if you just face a problem that like this one, right? So we just regard this one is f of x, this one is g of x. So we just find s squared, then this is f, then f prime will be 2x. F double prime will be 2, then f triple prime will become 0, right? But for g of x, this is g. Original g prime x is e to the power of x. This is g prime x, right? So then we try to get g. Ex integrate one time, ex twice, still ex, and 3 times ex, right? Then we just cross it here, times together, times together, times together, times together. Then here will be addition of plus minus plus minus. So finally you can get the result will be s squared ex minus 2x ex, then plus 2ex, then finally this term will be 0, and you need to xc, right? So this is the tabular. Actually, tabular is not a new. It's also based on the integration by part. But you can just list out f and its related derivatives, and g of with its integrals, then just cross terms together, then you can get the result. Okay, so let's just stop here. As for the day for our first quiz, maybe I will think about that because some students have some another agenda next Thursday. Maybe I consider next. How about next Monday? 刚那个同学